So a very good morning and a warm welcome to the second day of the workshop. So we'll start today's section with the talk by Dr. Srikanth Rangarajan. So he's a research professor in the Department of Mechanical Engineering, Binghamton University, USA. So he joined Binghamton University in 2018 as a postdoctoral research associate with Professor Bhagat Samakia. He received his PhD degree from IIT Madras in 2013 in heat transfer, specifically in the thermal management and optimization of phase change material-based heat sinks under Professor C. Balaji. His research work includes liquid cooling in data centers, three-dimensional integrated circuits, and associated optimization.
Good morning, everyone. So it gives me a great honor and privilege to be a part of this workshop. And today I'm going to actually present on the thermal management of electronics. And so the agenda looks like I'm going to start with an introduction. And I'm also going to talk about the evolution of electronic packaging and thermals. And we're also going to talk about the new age problem and targets for electronics thermal management and limits of some of the cooling technologies and the fluid selection and some case studies on improving system energy efficiency, and a case study on the pump to two-phase cooling at component and system level, and then the transient thermal management using phase change materials on real devices, and then the limits of embedded cooling technologies, the future directions, and summary. So introduction. So climate change, as we all know, has been really alarming, and the amount of CO2 emissions we have been witnessing has been in a really high range. And the mitigation strategies are very clear that we have to increase the sinks, reduce sources, and energy efficiency, renewables, and carbon sequestration. And we are also seeing that this has become a real problem. And with whatever technology we are working, the climate change has to be a part of at the objective. So electronics, the pervasiveness and ubiquity of electronics equipment, because it has become inevitable in the modern day life. And from smartphones and laptops to appliances and wearable devices, electronics are becoming integral of everyday's life for communication, work, and entertainment. And the Internet of Things and 5G and AI further amplifies that the electronics are going to become more and more important. So sustainability and the environmental impact of electronics is something that has been a concern in the modern day literatures. And we see from this particular news that was published in the Nature that it really forecasts that electronics are going to become really consuming a lot of energy, especially with networks, data centers, and consumer devices. So the thermal management really becomes very important for one reason, that it improves the reliability of the electronics. And there is one other prime reason, is that it is also going to make the electronic chips more energy efficient by reducing the total power the electronic chips consume. So I'm going to touch base upon those fundamentals in the coming slides. So the electronics industry forecast. So what does the electronic industry look like in terms of GDP? And we are seeing that the electronic industry is rapidly growing. And to that electronic industry, we are seeing that there are different contributors, starting with 5G, AI, and data centers, and cloud automation. And it is always forecasted to be on the rise. And as I was showing you in one of the previous slides, it is estimated that the electronics is going to consume close to 20% of the global electricity demands in a decade or so. So the evolution of electronic packaging and thermals. So this Moore's law, which we have been discussing for more than 5 decades, it has been telling us that the more the transistor or more the components we can keep cramming onto a particular silicon space, the performance is increasing. But there has been a point where we have also seen that the frequency has started to plateau, and which means the voltage is also starting to plateau, and which means there is a constraint that comes up when we are trying to extend the Moore's law. And there has been a decade of effort that have gone in to sustain the Moore's law. So dark silicon issue. So the dark silicon issue has been a really big issue in the past decade, where a lot of people have tried to really overcome this. So as we can see here, it really starts with high power density. And having a chip with high power density also induces a high temperature, which means it's a thermal issue. So with the limited cooling solutions, if you're not able to operate or remove a certain amount of power, then the dark silicon really emerges. So the dark silicon basically is having only a certain portion of the chip to be active, and the certain portion of the chip becomes inactive, which means a forced inactivity can become a low performance from a chip side. And to increase the performance, you have to really do the transistor scaling. And once we do the transistor scaling, which means we are trying to have like an advanced technology node, that also induces a leakage power. So when the leakage power is induced, again we arrive at the same point where we started, which is the high power density. So this seems to be on the loop, and we are seeing that the high power density is really the problem, is the bottleneck with the dark silicon issue. And the projections on the dark silicon, when we look at it, it's really, really frightening, because from 45 nanometers to 8 nanometers, we see that the amount of dark silicon space in a chip has continued to grow. And it seems like most of the chip might stay inactive. And this was the projection from the ITRS that was published in 2015. And heterogeneous integration, that's a promising technique that people have followed to really resolve this dark silicon issue and sustain Moore's law. So the chiplets add another level of flexibility, because the chip size can be really, really adjusted according to any condition required for a particular function, which means that the unused part of the silicon can be made into a separate chip, and that can be used for that functionality alone. And the ability to package more function on the chip is weakening, but the power consumption is also shrinking, which means the performance is also shrinking. So the chip manufacturers are now looking for advanced packaging to continue to reduce the power consumption and improve performance. But what is the real challenge with thermal management here is that now to turn on all the functions on all the time to maximize computing performance is still a very difficult problem. So this is the question researchers should work on, because it generates a lot of heat and you can't deal with it anyway. So heterogeneous integration solves the dark silicon issue, but it doesn't seem to solve the thermal issues. So I try to collect some of the materials from a lot of sources, and try to make a chart on the evolution of transistor, packaging, and thermal solution. So it really started with 1904, where the vacuum tube diode was first invented. And then in 1926, we had this field effect transistor coming into picture. And 1935, there was a very interesting document that was published on the air and liquid cooling of vacuum tubes. And 1955 marks the year where the NASA first published its first document on the electronic cooling. And in 1963 marks the year where IBM really came out and had this air and liquid cooled heatsink commercialized. And the amount of heat per chip that time was 0.3 watt per chip. And in 1965, we had this Moore's law coming in. And we also had a transistor technology of 10,000 nanometers. And in 1980, we had this seminal work from Tuckerman and Peace from Stanford, who came out and published a paper on silicon embedded liquid cooled microchannel, where they were able to see 790 watts per centimeter square of heat flux being removed. But the caveat is it never made it to the commercial market. So still, people are trying to figure out a way if we can really make this to the commercial market because of its attractive heat flux removal. In 1987, we had this first IBM immersion cooled Cray 2, which was by FC72. And we also had this IBM's multi-chip module in 1987. And in 1990, we had this IBM's first jet impingement cooled modules. And we also had this 500 nanometers around this period. In 1993, many of the semiconductor manufacturers and companies came out and then first announced that the thermal interface material was identified as a thermal bottleneck, which means that when most of the cooling solutions have saturated, the thermal interface material was identified as a thermal bottleneck. And there was a decade of work trying to scale the transistors and then improve the performance and then trying to look at different cooling solutions. But beyond this particular 45 nanometer transistor, the people started to notice the leakage power was trying to rise. So when we are trying to scale the transistor, we never really got any advantage of the performance, and the leakage power rising became a problem. And that's the point where the Dennard scaling law started to fail, because it was never expected that the transistor scaling would actually have the voltage to be constant, because beyond a particular point, the leakage current was rising. And in 2000 to 2010 really marks the era of dark silicon, So this is the era where people started to really have a localized or a particular part of the chip to be active and particular part to be inactive, which means they were compromising on the performance because of the thermal bottleneck. And in 2010, really the heterogeneous integration started to become very popular. And we had this 22 nanometer technology around that time with the 300 watts per centimeter square chips being very prominent. So before 2010, the bottleneck that we had was packing more transistor advanced nodes on a silicon chip through transistor scaling, which means the Moore's law was sustained. And then after 2010, what was happening was very similar, but in a different scale. So we were packaging more silicon chips in a given space rather than packaging more transistors. And from 2011 to 2019, we saw like a huge advancements in transistor scaling coming up to like 5 nanometers. And we also saw that in 2021, after the heterogeneous integration was in full scale, again, the semiconductor companies came out and announced that the thermal interface material was becoming the bottleneck again. So this has repeated itself, and now we are in a very big challenge to either find a very good thermal interface material or to find a cooling solution that doesn't require a thermal interface material. Because as you can see now, the heat flux limits in 2021 was around a kilowatt per centimeter square. And this 2011 to 2021 is really the era of heterogeneous integrated packages. And now in the future, we are seeing a lot of AI workloads, and DARPA and Department of Energy and many semiconductor manufacturers have come and said for very, very specific application, they could see heat flux around 5 kilowatts per centimeter square, which is really frightening and poses a lot of challenges to the thermal engineers. And what is this era is going to look like? So from a lot of projections, this could be an era of embedded cooling, where you are going to try to bypass the TIM and have the cooling solution within the chip. And a lot of academic literatures are trying to come out, and we have to really wait and see if this gets commercialized or not. So for example, 4 5 decades before, heat becomes increasingly higher. And then in 2010, heat becomes a packaging constraint. So now the heat and the packaging have an interplay. They become entangled and they are becoming inseparable. And today we are seeing that heat becomes increasingly higher. That's not the only problem, but it also becomes increasingly inaccessible. So the huge deviation between the maximum and the average temperature and the heat becoming inaccessible is a real problem of this decade, especially with the packaging getting more and more complex. So the real problem of today's electronic thermal management. So how does today's package looks like? So is the heat really accessible? So what the picture or the schematic that you see here was published by the National Institute of Science and Technology, where they came out and said today's packaging can be as complicated as this, where you can have like a cage or a memory or a logic sitting on top of the processor, and then you have a lot of these interfaces, electrical connectivities, TSVs and all sitting there, and then you have your heat sink or your cold plate sitting on top of all that. So the region where the heat really gets generated has to pass through a lot of these packaging materials to really get to the coolant, and that is becoming a real challenge with heterogeneous integration. So thermal and hotspot challenges, power delivery challenges has been listed as one of the major problem of this decade for electronics. And as this packaging becomes more and more complex, because we want to increase the power density per unit area, so that is going to become a problem that is going to be on the rise. So spreading and moving the heat is becoming increasingly essential. So people have started to look upon packaging and thermal together, and they are looking for materials in packaging that can really spread the heat, or integrate any of the spreaders or heat movers into the packaging so that they are getting the heat to be accessible by the cooling fluid. So optimization opportunities for heterogeneous integrated packages can look like something like this, because you have your active device or your cores or your multi-chip modules at the bottom. And here is where the real heat gets generated. So in a transistor scale, the heat is really getting generated when the switching happens in the channel, and that has to come all the way to the active device. And then you have this thermal interface material 1, which is the TIM 1, and then you have this package, which is an integrated heat spreader or the lid, and then you have this thermal interface material 2, and then you have your heat spreader, and then you have your cold plate. So this all becomes a series of resistance. So if I want to look at the different technologies where my cooling can be really implemented, so I start with the technology one, which is embedding the cooling solution onto the device, which is very attractive from an academic standpoint and from a heat transfer potential standpoint, and it is also posing a lot of risk. So if we look at the different fluids that can be employed, we cannot employ liquid water so easily at the scale because it's because of its dielectric properties. So we have to rely on low thermal conducting fluids, and that becomes the real problem. So on the right hand side of the screen, I've listed all the desired objectives, and on the left hand side of the screen, I also have the constraints. So this technology one is impeded by the fluid that we can use, and the technology two is quite attractive because you're embedding the cooling solution onto the package lid, which is the integrated heat spreader. But the problem here again is that we can still use liquid water, but we are constrained by the surface area that's available. And the technology three is a standalone technology for the heat spreaders, which could be like a heat pipe or a vapor chamber, and that is going to be increasingly important. So what we desire is a high thermal conductivity and a very high dry out heat flux, because once the heat spreader, like a two-phase solution, like a vapor chamber or heat pipe sits here, then it's always going to be dictated by the dry out heat flux, and that becomes the maximum heat flux that we can handle. And the technology four is going to be the heat sink or the cold plate that can be on top of this heat spreader, and that can be a parallel flow or an impingement flow. Here we don't have any problem with the surface area because we get a lot of surface area. We get to use liquid water for our cooling. But the problem is that the amount of cooling that can really get access to this heat source will be limited after a particular point. And on the left hand side of the screen, I'm also showing the direction of increasing energy efficiency for cooling. So more we move towards the silicon chip, the more energy efficient our cooling becomes because you can remove a lot of heat. And the more we move away from the chip, that's also the direction of increasing reliability. So we want to really balance both the reliability and also the energy efficiency. So we have to really look into the packaging and the thermals more carefully. So the new age targets for actively cooled electronics. This was recently published by the Department of Energy, and they say that we want to really minimize the cooling power ratio of the cooling power to the IT power less than 5%, which is like also towards the zero carbon, zero water targets. And they also want to use low GWP targets, right? So you want to use a fluid that is also environmentally safe. And we also want to minimize the Kelvin per watt at the die level, which is the resistance, and the Kelvin centimeter square per watt at the chip level, and Kelvin centimeter cube per watt in the system level. So this Kelvin centimeter cube per watt is a new age metric that is getting a lot of prominence. And this was first introduced by Professor Bar Cohen in one of his early literatures, which was published in 2000s. And he really emphasized on using Kelvin centimeter cube per watt as a new age metric to optimize. And the target resistance at the die level today looks like you have to achieve like less than 0.01 Kelvin per watt for fluxes above 500 watts per centimeter square, which is really stringent and really aggressive. And also there is one thing to note, that for next generation of electronic systems, the IT power will become a function of the cooling power. This kind of a relationship, when we go back to this first objective, which is the cooling power to the IT power, then there is a real nice optimization problem, because the more you maintain the IT's temperature lower, which means you're also going to save upon power of the IT's operation, which improves this ratio as well. So there is an optimal value that can exist, and that will become really important in the coming days. And people for that reason are also looking into subambient cooling. If you can really make your chip's temperature less than the ambient, then you're also making your IT more and more energy efficient. So this is where the packaging and the cooling becomes entangled. And let's also look at some of the cooling limits that we have proposed in the recent years. So here we have tried to arrange what the commercial cooling techniques have been trying to do with respect to the complexity, cost, and risk, which is arranged in the y-axis. So we see that the forced air cooling can do up to 100 watts per centimeter square with advanced thermal interface materials, vapor chamber, heat pipes, and optimized heat sink. and we also have the single phase liquid and the two phase refrigerant cold plate, and then we have this immersion cooling, and then we get to the embedded cooling. So the embedded cooling is where the Tuckerman and Pease in 1981 had already had a ballpark number of 790 watts per centimeter square. So we are also looking for techniques which can really bypass that, and there are some recent papers that have done that. So that's, I'm going to show that in the coming slides. And also we have 4 single and 2 phase liquid cooling with printed fins on chip, like additively manufactured fins sitting directly on the chip, which also eliminates the thermal interface material. So from our group in the last 3 years, we also tried to define some of the heat transfer limits for air and single phase liquid cooling, and this has been published in the IEEE's roadmap. And we see that for advanced multi-chip air cooling with integrated vapor chamber, we are seeing a heat flux close to 55 watts per centimeter square. And for water cooled, which is also having like a very stringent microchannel design for single phase, we are seeing somewhere close to 170 watts per centimeter square. And this is the air cooled heatsink that we have tested that is integrated with a lot of these two phase solutions like heat pipes, and also it has a vapor chamber sitting in the bottom, which really helps to spread and move the heat. And this is the limits that we are trying to see today. So again, when we talk about the limits, these are some calculations that we have got from both experiments, numerical and theoretical calculation. And on the left-hand side, we are showing the theoretical limits for air cooling. And on the right-hand side, we have the theoretical limits for the single-phase liquid cooling. And if you follow the yellow curve on both of these plots, which is the heat sinks resistance, you see that the air cooling with its advanced enhanced ratio, area enhanced ratio, which means as the air cooling heatsink can become more and more bulkier, we see that it can maximum get up to, let's say like 0.5 or 0.3 Kelvin per watt, because area enhancement ratio of more than 30 might not be really, really desirable. But when you look at single phase liquid cooling, we see that it can start from anywhere from 0.1 and get very close to 0.02 to 0.03. So which is again really, really good, but more the enhancement you make, it can really come to 0.015. But both of these are seen to not achieve the targets that we saw in the previous slide, which is really lesser than 0.01. So theoretically, air cooling and single phase liquid cooling have reached their limits, and now we have to look for really, really exotic cooling solution to achieve the new age targets. And for air cooling and liquid cooling, there are some huge opportunities. So this is a like a breakdown of the resistances that we have. So for air cooling, we see that the heat sink is still a big resistance, the blue shaded region, which means you can still integrate a lot of this advanced heat pipes and vapor chambers and then try to move the heat. And on the right hand side, for liquid cooling, we see that the thermal interface material really dominates the resistance. So that has to become the future. And for fluid selections, we have tried to use the fluid selection correlation published by Saylor and Professor Bar Cohen. And we see that the water is a superior fluid among all the fluids that have been investigated. And also we are trying to arrange some of the dielectric fluids, and we see that the Novec and FC72 are becoming more and more popular today. And because of the New Age Act, we are also waiting for the new fluids to come in, and we are looking forward to arrange them in these kind of plots. And now, though the air cooling seemed to have reached its limit, we have done some studies in our lab for a feedback-based cooling systems. So for an air-cooled server, we have taken the server from Dell R520, which is a 2U server. And then we have these two heat sinks sitting on top of the CPU. And then these CPUs are cooled by sits fans. So this is exactly what happens in a server, where like the heat sink are sitting right next to the fans, and you have sits fans operating, blowing air to these heat sinks to make sure that the operation is really, really reliable. And we did try to optimize this particular fan control algorithm itself. So in the backend daemon, we are running some workloads to induce some IT loads, and then we are trying to record the CPU temperature, inlet temperature, power consumption, fan speed. And what really comes out of that is that as the power consumption utilization of the CPU increases, we are also seeing the fan speed is readily increasing, which means it's a very smart system, but the question is whether it's an optimal system. So this uses the Intel chip. We have two CPUs, and what we have observed here is the interesting data on the power. So this blue curve really talks about the total power consumed by the server. And we also have the fan power indicated in orange. And we also have the power usage effectiveness in the bars. And we see that this power usage effectiveness is nothing but 1 plus cooling power to the IT power. And we see that this is smart, but really not optimal. So there is a huge opportunity existing in the air cooling region where you can try to optimize these kind of response between the fan and the chip to make the systems more and more efficient. So the target is, if you're able to stress all the cores and if you're able to operate your IT at its maximum efficiency, and if you're able to reduce the cooling load, then it becomes more smart and more optimal. So that's going to be the roadmap for air-cooled heat sinks. And the next study, what we have done is a thermal aware core hotspot alignment in three-dimensional integrated circuits. So the three-dimensional integrated circuits are becoming more and more popular. And we have done some studies which is based upon AI. And we had this three-stack three-dimensional integrated circuits with different hotspots of different sizes and different flux and dissipating different power. And we wanted to really optimize the position of these hotspots so that it becomes a thermally aware design. And we are not looking at the electrical point of view for now, but we wanted to conduct a pure thermal design to really quantify the crosstalk that can happen between the hotspots in a die and the crosstalk that can happen between the hotspot between the dies. And for this purpose, we had to define a lot of these arrangement parameters that the AI can really take in as an input, and then it will be able to understand that a particular arrangement means a particular value, and it will be able to optimize it in a better way. So this was a sampling algorithm developed by our lab where we can have accept and reject the samples based upon specific conditions. And we made sure that we are able to self-automate this particular design. And this automated design was clubbed with the genetic algorithm. And we wanted to find out what is the optimal arrangement that can really reduce the hotspots in a chip. And what we see here is this particular design. So this particular design really become the optimal design. So the numbers that you see on the top of this are nothing but the die number and the hotspots number in that particular die. And we also had a liquid cooling experiment that was conducted in our lab. And then we tried to derive the locally varying heat transfer coefficient, which was given to this numerical model. And you can see here that the AI was really able to predict the optimal design when it was clubbed with the genetic algorithm. And this becomes the optimal design where you see a much uniform temperature. But for other designs that we tested, you can see that it is becoming more and more non-uniform, or it's uniform, but it's of higher temperature. And we validated one such case with one of our experiments where we had like a test package of 2 layers, and we tried to see if the model works, and it really works. So this is the thermal imaging that we had, and we also were able to get an optimal solution. And the next research that we are trying to do in our center is a pumped two-phase cooling at the chip level and rack level. So the pumped two-phase cooling today is very attractive because, as I was mentioning in my previous slides, air and liquid cooling are reaching its limits, which means we have to really go for the next generation two-phase pumped cooling. And the real attractive thing about the two-phase cooling is that it allows absorbing heat at a desired temperature by controlling the system pressure, because the two-phase cooling is really useful when you're considering a big system or a rack level system. And we have developed our own bench level facility to have this flow boiling experiment happen. And we also have a mock heater that can generate up to a kilowatt of heat. And we have the cold plate sitting on top of it. And we have done like extensive experiments from commercial cold plates, because the member companies that we work with are really interested in knowing if a particular commercial cold plate is really optimal or not. And we have taken a lot of geometrical data. So the original product design can look something like this. And we have gone ahead and then tried to reduce the height of the fins, height of the channels. And then we did see that the thermal resistance was dropping with geometry. And then we also tried to cut the channels and make it look like a pin fin. And then we saw that the heat transfer coefficient was immediately jumping. And we had the modified design getting a much higher heat transfer coefficient compared to an original design. So these were some random studies that we did on geometry, but we really wanted to do like a very specific optimization on the geometry. And we did go to the neural network. So as we saw that there are a lot of correlations that are available for flow boiling, but we wanted to develop a machine learning model just very specific to this particular cold plate at a very specific operating condition to test and see if you are able to really generalize this problem. And the cold plate geometry parameters really went as an input, and then we also had the cold plate response parameters as an output. And we have successfully built this neural network, and we have also done a multi-objective optimization. And then we did arrive at designs that can be like very efficient with thermal resistance and also very efficient with the pressure drop. And we can also try to flip this optimization problem to find out the worst design as well. And we did find the best and the worst designs, and then we validated one of the designs that we got here with an in-house experiments, and we are continuing this study to make it more general to more operating conditions. So this geometric optimization study was quite successful, and we are continuing to do this. But in the meanwhile, we also wanted to take the original cold plate and put it in a rack. Because the rack level dynamics are very different from what you can see in a bench level dynamics. And this is an in-house data center at Binghamton. And we have a dedicated rack that was previously air cooled. And we replaced all the air cooled heat sinks in this particular rack with a liquid cooled cold plate, and which was two-phase. And we had a coolant distribution unit that was comprising of a reservoir and a heat exchanger and a centrifugal pump. And we also had this particular modules going through the manifold and then delivering the fluid to each of the server. And you can see here the servers are arranged vertically, and we have this coolant distribution unit having a common manifold to distribute the fluids. And we saw something very interesting. So when we are able to regulate the system pressure, the subcooling really reduces and the rate of vapor generation goes up, and it induces a resistance on the flow, and then the flow rate reduces. So we were able to readily see which servers were undergoing boiling and which servers did not undergo boiling just by measuring the flow rate. And one other thing is that an optimized cold plate, when we put it in a rack-like system, might not become really optimal because there's a lot of interactions that can happen, and we have seen that here. So in this, we can see that because of the flow distribution, there are some racks, some servers that undergo boiling, and there are some servers that do not undergo boiling. And that is because of the hydrostatic pressure difference and also the pressure that gets induced at different inlets. And this really becomes a flow control problem. And we are continuing to investigate that in our coming studies to see if we can have a boiling that can happen in all of these servers, but that also can induce a lot of problem because the vapor quality will simultaneously increase at the exit. So the temperatures of the CPUs before and after stressing them, we have noted them, and we have seen that whichever server has undergone boiling had a reduced temperature or a slightly increase in temperature, but other CPUs had a very high temperature. So we are also looking into phase change material-based capacitance for portable electronics. And the real challenge with the phase change material is like we should be able to absorb a lot of this heat flux that comes in as an impulse, and we have to absorb the peak load without increasing much of the temperatures. And today there are a lot of literatures talking about the multi-objective optimization of the phase change materials, where they are trying to simultaneously optimize the melting cycle as well as the cooling cycle. So for selection of PCM, we have a lot of this performance metric defined in the literatures, but what we want to really look at is the thermal conductivity and the latent heat, which is a combination that we don't get quite often, but we want to have maximum of both. And there is a lot of this figure of merits that have been defined in the literature, but we would really want to extend the time of operation. That's the main thing that we are looking at. And we have published a study where we are also trying to look at the limits of phase change material-based composite. It's not always optimal, and only a metal can become optimal with certain heat flux and amplitude and frequency. And that becomes really, really interesting, which means there is a limit with which you can use a phase change material. And today, we are also trying to test the phase change material on real devices, because the dynamics in a real device could be really different from a characterization experiment. So this is an effort that we are trying to make, where we are fabricating porous foams, and we are trying to put in PCMs in a portable electronic device which is real. And then we are trying to induce workloads by its operation, and then we are trying to see whether we are able to get a reduction in temperature. And yes, we do see a very nice reduction in temperature between the cases with a PCM and not a PCM, but it also requires a lot of spreading. That's exactly what we are observing in these experiments. Like, the heat is really localized in a portable electronics. It just sits in one corner, and we have to really spread the heat and then get to the porous composite where the PCM gets access to the heat, and that becomes the real studies. So, and then the cooling limits on two-phase immersion and embedded cooling. This is a literature survey that we have done as an effort to understand the future directions. So immersion cooling is gaining a lot of momentum. And as you can see here on the y-axis, we have the heat transfer coefficient, and on the x-axis, we have the critical heat flux. So we want to maximize both. That's going to be the new age problem. And we are seeing that using liquid water is really highly efficient, because that really tops the chart. Like the study is done by Professor Satish G. Kandlikar in 2014, where using liquid water is able to get a heat transfer coefficient of close to 100 watts per centimeter square Kelvin. But using dielectric fluids really are very close to like 50 watts per centimeter square Kelvin, and then we are getting heat fluxes very close to 150 watts per centimeter square Kelvin. And we also have interesting studies using liquid water, where they are trying to use an insulating dielectric layer to avoid contact, which means the water is in direct contact with the electronics, and people are able to achieve a critical heat flux close to 500 watts per centimeter square. And with respect to immersion cooling, there is an emerging area with additively manufactured boiling enhancement coatings that are becoming really, really attractive. And with respect to silicon embedded cooling, that is also going to be one of the future directions for electronic cooling. We are seeing that the Tuckerman and piece have already been surpassed by one of the studies from IBM, where they have really, really rooted the fluid onto the silicon. And then we have got like heat flux more than 1000 watts per centimeter square with a temperature rise of close to 50 or 60 Kelvin from the chip temperature. So we are also seeing a lot of other studies which have been done in the past decade that they are trying to use the silicon itself as a medium to cool and routing the fluid through that. And with different chip sizes, we have really arranged this chart to get an overview of how the chip sizes along with the fluid, along with the embedded cooling, what is the maximum capacity that we are able to achieve. And today, there is a lot of groundbreaking works that are happening around the world. So I just wanted to list these two works that really catches our attention. So one is the illustration of by the researchers from UCLA, where they have developed a solid state thermal transistor using electric field to control heat movement in a transistor level itself. And this seems very interesting, and we have to really wait and see if this becomes really, really practical. But in that article, they have mentioned that there is a way to move the heat by using a solid state thermal transistor. And there are also some studies using a passive salt water cooling, which seems to boost the CPU performance by almost 33%. So some of these groundbreaking works are also happening. They are looking for a different kind of cooling, different type of embedding the cooling solution, getting onto the transistor level itself to remove the heat. And there is also a great initiative in India. So India is also on the path of becoming the global leader in semiconductor manufacturing. And thanks to our honorable president, Sri Narendra Modi, for having this initiative. And thermal management of electronics has been identified as one of the among the 12 strategic research areas that we have to take for the India semiconductor mission to become successful. And it's a really a golden period around the globe for people working on electronics and thermal management. So in summary, the initiatives are at the forefront of research and development, pushing the boundaries of what can be done today and what needs to be done in the future. And by focusing on innovative approaches such as microfluidic cooling, advanced materials, and smart thermal management techniques will revolutionize the way we manage the heat. And as we continue to ask more from the devices, whether it's in the high performance computing or AI or data centers, we must remember that the efficient thermal design and cooling systems are the unsung heroes that make it all possible. And heterogeneous integration will drive the technology for the foreseeable future, and they will bring new power challenges and new thermal challenges and also increase performance. And machine learning driven multi-objective optimization will enable global optimal solution, be it packaging or thermal management. And this is a quote with which I really wanted to end my talk, which really caught my attention recently from semiengineering.com, where they said like, we can design and manufacture incredible chips, except they will melt. It is no more a manufacturing limitation, not a design limitation, it's a thermal limitation. So thermal is becoming a limitation for chip manufacturing and chip design itself. And we have to get more and more heat out. So thermal management is actually on the forefront. And I would like to thank you all for your attention, and I would welcome any feedback or questions on my talk. And this is the data center at Binghamton University. I just had a photograph there, and on the right-hand side, you can see our recent book chapter that was published as a part of the book that was edited by Professor Justin Wabel and Professor Mehdi from Stanford, which is talking about the embedded cooling of electronic devices. So thank you all for your attention, and any questions or feedback.
So very interesting talk, talking about the most recent trends in electronic cooling, Srikanth. So we will take some questions from the audience for the next few minutes. Any questions?
Hello.
Hello. Hi.
Yeah, it was a very nice lecture and throwing the lights on the some recent advancement in the thermal management of electronics.
Sure.
You have used at one point of time that circular microchannel, and if we see the aspect ratio being along the path of this fluid, there is a maldistribution of fluids. So, what made you to go with the circular microchannel rather than going with the rectangular microchannels?
No, it was actually a circular base, but the microchannel wasn't circular actually. So the channel wasn't really circular. It was the normal microchannels that we see, but it was a circular base, but not a circular microchannel. I'm sorry, I'm not able to hear. I'm sorry, I'm still not able to hear.
Hello, Srikanth.
Yes. Yeah.
Good morning,
I'm able
Srikanth. It is Sangamish here.
to-
So
Good
just I
morning.
have see, as you can see that the sizes of the transistor or the electronic components going down and are smaller. But how you suggest about performing an academic research on those things? Because in the laboratory or the academic research, that small scale manufacturing is very difficult.
Exactly.
So
Exactly.
then
I mean,
how-
that was a very nice question. Yeah. Because for the new age electronics especially, we still continue to conduct experiments on a lab level where, like for example, if you can mock a device, let's say you have an electronic device that is like 1 centimeter by 1 centimeter, even if you're able to mock the device and then propose a new thermal management, but that doesn't really give you some insights about the sustainability aspects of this electronic cooling, because only if we work with the real electronics, then we'll be able to really understand what the thermal management does to the IT consumption, IT power consumption of that electronics. Because we are seeing readily that some of the advanced chips that are doing with AI, once we have a liquid cooling that is coming on, we see that the power consumed by that IT itself is reducing. So which means it's more in the sustainability part. So the lab research that we are trying to do with, let's say, if you're not able to get a even small heater, we won't get any insights about how the thermal management is making the electronics sustainable. So I think it is now the time that we really work with real electronics, and that way we can get a lot of ideas. So that is going to be the path forward.
So it means the smaller of electronic components, and it is difficult to perform the laboratory mimicking those things and doing the laboratory experiments.
Yes, I think you can still mimic and get your heat transfer coefficient by doing a lot of this thermal experiments or modeling. But the problem is you will never be able to understand the IT performance side because of the thermal management. So that's exactly why I wanted to highlight that your IT load is going to become a function of your cooling load. And the path towards sustainability is to report both the IT power consumption and the cooling power consumption. Okay. And if at all we want to conduct an experiment on really small electronics, if you want to mimic, I think some additive manufacturing techniques I've seen where people are trying to really produce smaller parts, and you can still conduct your laboratory experiments.
Thank you, Shekhar.
Thank you. Thank you.
Hello, Srikanth.
Hello.
It was very good talk, and
Thank
overall briefing was very good. I have two questions. So first
Sure.
thing is related to the slide which talks about transient case for a
Yeah.
server cooling. There you were telling that for boiling rate, you are referring to mass flow condition, and you are controlling that
Yeah.
through that curve. So there, I just need a clarity. And second point is whatever work you have done, it is through industrial collaboration, because the chip industry is so dynamic. So it is changing so drastically.
Exactly.
So how exactly is that your research works are directly collaborated with the industry and taking the latest problems and dealing with that? So
Okay.
could you comment on this as well?
Sure. So answering your first question, like in a rack level, once we try to install our cooling solution, the one thing is like we made sure that every server is subjected to the same heat load. So with respect to the thermal boundary condition, we stayed uniform. And then there is a manifold that is distributing the fluid, which means because of the height of the manifold, there is a inherent hydrostatic pressure that's there in the system, which is also going to change the inlet saturation temperature for the fluids, because the saturation temperature becomes a function of the pressure. we are seeing that because of this all dynamics and big interactive system, there are certain servers that undergo boiling, and there are certain servers that are not undergoing boiling. And in the servers that are undergoing boiling, because it boils, because of the vapor generation at the exit, you have a friction and then there is a flow resistance. And because of the flow resistance, the flow rate really drops in those particular servers, and the other servers have a good flow rate. So in the inlet, it's not a very big problem. But what happens in the exit is really, really a big problem, because in the return, you have different flow rates and different vapor qualities. And if there is one server is going to generate a lot of vapor quality, and let's assume the other servers don't boil much, so there is no much vapor quality. So when all of these gets condensed in the common reservoir, we want to make sure at the end everything has become liquid, everything is condensed. So these are the the flow regulation really, really becomes important at the inlet, because at the exit you want to make sure everything is uniform. And for that, we are trying to do some inline heaters and flow regulating valves that we are trying to construct, which is ongoing work to make sure that we have some uniformity in the boiling as well. So
For all these
that's
servers, for all these servers, different regulators will be connected. For all
no,
these
we want to
servers.
have yes, different regulators, which takes input from one common system. So it gives feedback to one common system, but there is local regulators kept for every server. That's perfect. Yeah. And answering your second question, you're very right, because the electronics are really, really changing. Today, we are posed with a challenge that, whatever comes today, we are trying to do our best to propose a thermal management strategy, but the architecture and everything keeps changing. And we just want to make sure we are staying up to date. And at least for a year, things don't change much. So we try to work on it, learn a lot from today's electronics, that really becomes a prior for what you want to do for the next generation electronics. So that's the way we are trying to progress.
Hello, Srikanth, very nice presentation. My name is Anand. Actually, one question. So recently, we heard in the news that the USA is throwing iPhones, because of heat dissipation is more from the portable, as you presented in your presentation. How the PCM technique is challenges in portable electronics components, and how we can come over it from the heat dissipation. As
Okay.
India is moving Atmanirbhar Bharat, so and as you told in the Prime Minister Narendra Modi has also initiative. So how we can moving forward these the generation of heat challenges in the electronic components.
Yeah. Okay. A very nice question, because the real problem with the portable electronics, not from the chip side. If I look at it from the external side, the real problem is the cooling conditions are constantly changing. The ambient condition, the heat transfer coefficient are constantly changing. And today there is a great research that is going on the challenges of having a back case on your portable electronics, because that also impedes the way you can dissipate the heat. And what we see with the phase change material is its opportunities is that it can only absorb an excess power, a transient, but at the end, the PCM has to dissipate the power to the ambient, which is now being impeded by the back case and the leather covers that we have on the portable electronics. So the portable electronics region of electronics is very, very challenging to cool, because of its varying boundary conditions in the ambient, and also the power surges. Do they come and go? I think the main problem would be the spreading. So if you're able to spread the heat, get it to the PCM, that's 50% of the problem. But the main problem is, how do you get the PCM out? How do you get the heat out from the PCM to the ambient with the varying ambient condition as well? So that is going to be a real problem. And I think there is a huge opportunities with portable electronics for phase change materials, especially vapor chambers and heat pipes, because today we see a portable electronics coming out with heat pipes as well, which is moving the heat. So yeah, with heat spreaders and phase change material, I think there's a huge opportunity.
Okay, thank you, sir.
Thank you.
Just a final question, Srikanth. Your embedded cooling solution. So now you're talking about the heterogeneous integration, where you have different layers stacked on, top and three-dimensional architecture and so on. So how feasible it is to introduce embedded cooling. So then in this case, it becomes very complicated. So each of these components have to be embedded, and then you have a multi-dimensional architecture on top. So do you think that complexity in terms of cooling, not just cooling solution, but in terms of designing this for different architectures and so on will be?
Absolutely, Professor. Thank you really for raising this question because, as I was mentioning on the evolution chart, there's a seminal work by Tuckerman and Pease which is still sitting on paper. It has never been able to commercialize, though they were able to demonstrate that etching channels on the backside of a silicon can be very attractive, close to 790 watts per centimeter square. But the industries have always resisted such a change because no industry wants to touch silicon and have us routing the cooling through that. But what the industry also understands is that we are reaching the limits in every decade. Like in the decade of dark silicon, there is a heat transfer limit that we reached, and then we moved to heterogeneous integration. Now with heterogeneous integration, people have understood that the thermal interface material and the compliance is the main thing, and that is going to be the highest. Now, if people really want to remove the thermal interface material, the next step is to embed, but the embedding is very challenging, very challenging, because it also impedes with your electrical connectivity, and also the chips talk to each other both thermally and electrically. They communicate with each other, so nothing of that should be disturbed. And today there is a very interesting study that IBM is doing. Like, for example, the TSVs that really connect the two chips that are stacked on top of each other. If there is a fluid that really flows through the TSVs external, the signal integrity is lost by at least 25%, which means the signal transmission also gets affected because there is a cooling fluid. So we really have to isolate the cooling fluid, but also we have to embed them. That's a great challenge. And today the industries have slightly started to talk about it, but there are a lot of studies that are talking that introducing the cooling in the silicon can really disrupt the electrical signal integrity.
Yeah. So thank you, Srikanth. We actually have some more questions from the audience, but we are short of time. We have to move to the next speaker. So we once again appreciate a round of applause for Srikanth's excellent talk. So we have a small memento that we will send it across to you. So we will come back to you on that. So thank you once again for joining us. Thank you.
Thank you very much, and thank you, Professor Aravind, and thank you all for your attention and feedback. Thank you.
Professor Marco Marengo is our visiting professor here, so who is also a very active person in thermal management.
Yeah. Hi, Professor Marco. Your yesterday's talk was really inspiring. I took a lot of notes from that actually. Thank you so much.
Yeah, you can maybe stay back. He has another talk coming up on heat pipes.
Yes, I'm going to stay here. Sure. Thank you.
Thank you.